So today we have Thomas Steinke. He's a research scientist of brain team at Google Research. Before Google, he was at IBM Research, and he received his PhD from our neighbor, Harvard University, and working with Salil. He worked on a variety of the topics with a focus on differential privacy, and today he's going to talk about hyperparameter tuning with Renyi Differential Privacy. So without further ado, I'll ask Thomas to start his talk. Thank you.
Thank you. Thanks for inviting me. So let me just start with like a one-slide overview of what this talk is about. So in the ideal world, you have some differentially private algorithm. You run. Was someone saying something?
No, sorry.
Okay. So in the ideal world, you run your algorithm once and you publish the output. But unfortunately, what happens in practice is you're going to run the algorithm multiple times and you're only going to release one of those runs. And a very natural reason you do that is to try different settings of the parameters in your algorithm. So just as an illustration, you have your private data, you put it into your box, but the box has a lot of knobs and you're going to want to adjust those to get the best possible results. And I think at the moment, the standard is just to totally ignore this and only release the privacy parameters that would correspond to running the algorithm once. So the point of this work is to try and understand what is the difference between these two worlds. So what is the difference between running a thing a bunch of times and only reporting one output versus actually only running it once. So we have some mix of positive and negative results. So on the positive side, we do show that there's not a high privacy cost for doing this if you do it right. If you're a little bit careful, you can run your algorithm many times and only report the best outcome. And the privacy cost is going to increase. It's going to increase, but it's not going to be catastrophic. But if you are not careful, it can actually increase a lot. Okay, so what's the outline of the talk? Basically, I'm going to talk to you first about the negative results, which is essentially the motivation for the work, which is going to tell you about what happens if you aren't careful. Then we'll sort of give a precise problem formulation, and then we can state positive results. First, I'll talk about pure DP results, because those are a little bit easier to grasp. And then I'll tell you about the Renyi DP results, and I'll give you some plots that show what's going on. So I'll give you a preview of the pure DP results next. And yeah, please feel free to ask questions at any time during the talk. Okay, so I'm just going to give you a brief preview of what a positive result looks like for the pure DP case. So let's start with a bunch of differentially private algorithms. Now you could think of this as just being one algorithm that you run a bunch of times, or one algorithm that you run a bunch of times with different settings of all of the knobs on the algorithm. And we're just going to assume that each of them is individually epsilon differentially private. So what we can show is that there exists an algorithm that is 2 epsilon differentially private. So you've got a constant factor increase in the privacy parameter. And what it does is the following. So with high probability, when you run the new algorithm A, it's going to run each of those algorithms at least once. And it's going to look at all of the outputs and it's going to pick the best one and return that. Right? So we're able to, in a sense, run all of the algorithms with only a constant factor blow up in the privacy cost. So I'll just sort of highlight a couple of the features here. So the first one is that this is a black box result. So we're not making any assumptions on these algorithms other than they satisfy differential privacy. So not sort of like opening them up and applying tools that are going to depend on the internals of the algorithm. Now you may be wondering, what does it mean to output the best result? So this is going to be in terms of a self-reported value. So basically, I'm going to assume that each of these algorithms MJ outputs a score for its output as well. So we're going to assume that the algorithm outputs a numerical value that says this is how good my output is. So maybe that means maybe that means you need to allocate some privacy budget within the algorithm to evaluate on a test set or whatever and produce some kind of quality score. So you may be wondering, this theorem is a little bit vague. I have said with high probability. So this result works with an arbitrarily high probability, and it also works for any number of algorithms m. Now this seems kind of like it's too good to be true, and it sort of is. This is kind of a quirk of pure DP. So if you're familiar with the exponential mechanism, you know you can run the exponential mechanism with as many inputs as you want. It's still private. What you suffer is in terms of accuracy. So the issue is that if you run a huge number of these algorithms, then there is some probability, of course, that you get an erroneous high score, right? It's a self-reported score, so you have to have that being differentially private, and there's a chance that you'll make an error that way. So there is some cost here. There's also a cost in runtime, because I said it runs each of the algorithms at least once with high probability, but it could run them many, many times. And the higher the probability you set, the more you have to pay there. So I should mention the most related prior work is by Jinqing Liu and Kunal Talwar. This was in Stock 2019. And they proved exactly the same result, but with a factor of 3 instead of a factor of 2. And basically this work is very heavily building on that earlier work. Okay, are there any questions at this stage before I actually start going into more detail?
Thomas, is there no assumption about what constitute further structure on what is best? Meaning, if I just have a bunch of DP algorithms that output real numbers, let's say a single real number each, and I output the maximum, that's always going to be 2 epsilon DP?
Yeah.
Is that the claim?
Yeah. So all I'm assuming is that the output space Y has a total order on it.
Thomas, so there's like 2 algorithms in Liu Talwar, right? One is the 3 epsilon, one which is kind of like weaker, and then they do some sort of fancy stuff to get like down to 2 epsilon. Is that right, or something like that?
So in the Liu Talwar paper, they do have an algorithm that gets 2 epsilon, but it's a slightly different statement. So what they say, so here I'm saying I'm going to run all the algorithms, I'm going to output the best. There's a different formulation where you say, okay, I have some quality threshold that I'm aiming for. I'm just going to keep running algorithms until I finally get an output that exceeds that quality threshold. And that ends up getting you a 2 instead of a 3. So it's like a different problem formulation.
You need to kind of know the quality of the best thing in particular for that.
Exactly. You have to know in advance what you're looking for.
And Thomas, does it matter if the mechanisms are chosen in advance or adaptively?
It does, yes. So I'm assuming they're chosen in advance. There's no adaptivity here. So just as a comparison point, if I were to apply composition, I could prove the same result, but instead of a 2 epsilon, I get an m epsilon, right? So if I run each of these m algorithms, and I could output all of those outputs, I'd get m epsilon. So that would be sort of a trivial bound, and that's kind of the comparison point. Okay, so let me keep going. So maybe I should specify a little bit more what I mean by hyperparameters. So just in general, there's a lot of choices that you have to make when you're running the data analysis system. Of course, machine learning is the one that people often talk about, especially with the language hyperparameters. And there's sort of a lot of choices, like the basic one is which model should I fit? You know, should I do a linear regression? Should I do a logistic regression? Should I do some kind of neural network? There's also regularization. It's also important to note that differential privacy itself introduces some hyperparameters. So if you're doing clipping, for example, so you have to clip your gradients when you're doing stochastic gradient descent. The value at which you clip is also hyperparameter, along with the learning rate and all of these other things. So these are the choices. And it's typical to just do an automated search because generally you don't know in advance which of these settings is going to give you the best result. So it's common to just do an automated grid search where you throw an enormous amount of compute power to try all of these things in parallel. And yeah, this is what Kobe was asking. So in this work, we're not going to consider any kind of adaptive search or sort of a manual search where some human is involved. We're just going to consider the sort of grid search approach, the naive brute force strategy to hyperparameter tuning, which is what people do often in practice. Okay, so I assume everyone in this audience has seen the definition of differential privacy before. And was that a question?
No.
No, okay. So what we're going to assume again is that once the hyperparameters are set, then the algorithm is differentially private and we'll have some precise guarantee. That's sort of outside the scope of this work. We're sort of assuming you've already done that. But the question is just what is the privacy cost of those hyperparameters, what they are, what the information encoded in those. So let's start with the most naive approach you could take, which is that you select the hyperparameters in an entirely non-differentially private manner, and then you just have a final run where you use those hyperparameters to do your final run and report those values. So you might have this vague intuition that hyperparameters are a very narrow channel in the sense that you're typically only talking about a couple of settings or some sort of discrete choices. And in these choices are a function of many data points that are sort of aggregated. And you might have this intuition that there really isn't a problem here. Now, I assume that in this audience, people are not surprised that this intuition doesn't really work out. Like we're typically pretty skeptical as a community about claims that things are not a problem. But it's still good to like have an experiment where we look at this. So I'm going to look at the setting. We just take the selection of hyperparameters in a completely non-differentially private manner. But I should also know this is not a good thing that you should be doing, even from a utility perspective, because the best choice of your parameters might be different for a differentially private algorithm, the one you're going to run at the end, versus the non-differentially private algorithm that you're using to select those parameters. So this is something that's not good for more than one reason. Okay, so the intuition for why this doesn't work is that a single outlier can affect the hyperparameters. So here's just a plot with a very simple toy example. So all it is a linear classifier, so a support vector machine. And there's a regularization parameter, so an L2 regularizer. And basically you start with some data that is nice and well separated. And then you may or may not have two outliers. So we put in two outliers just to make it a little bit clearer rather than just one. And you can see in this plot that just the presence of two outliers in a data set of size 200 does change what the optimal, well, you can see a difference between the settings of the parameters, like which accuracy you get with which setting of the hyperparameter. So just to be a little bit more precise, this is just a two-dimensional classifier. Your positive and negatives are two Gaussians, nicely separated. We have 100 samples from each. And then we just have two outliers that are basically mislabeled by the obvious classifier. And the model is what you get from a support vector machine. So you've got a hinge loss and an L2 regularizer. And the parameter alpha just sets the weighting between these two parameters. So you can see that there is a difference in, you can see a difference in what happens here. Any questions about that?
So the attack here is that I would then you would release, say, your model with the accuracy and the parameter you used, and then I would draw a threshold and I would know.
Right. I mean, it's just a demonstration that a hyperparameter can be affected by a single, or in this case, two inputs. It's just a, I mean, the attack would be to basically, once you've released the accuracy and the hyperparameter choice, you can kind of see that this would change. And again, we're assuming here that you've not applied any differential privacy at all. So this is sort of like a straw man.
Mm-hmm. Okay.
Okay, so this vague intuition is not accurate, but I mean, we are going to show that there is a narrow enough channel that we can get good bounds for it if we do it careful. So as I said, this was entirely without differential privacy. All we've demonstrated is that those hyperparameters can be sensitive to individual data points. So the next question is obviously, okay, so this was very much a straw man. We've done nothing to protect the data. What happens if we try doing it with differential privacy? So I think the first thing you would think of is to apply some version of the exponential mechanism. Right, we've got a bunch of options. We want to select one. The canonical algorithm is the exponential mechanism. And this was actually something that was proposed in 2013 by Kamalika Chaudhry and Stahl Winterbo in Europe's. And basically, the algorithm is exactly what you expect. The main issue with this approach is that you're going to have to assume that you have some kind of low sensitivity function that is able to measure the quality of the hyperparameters. And in order to make that work, you're going to have to make some fairly strong assumptions about the algorithm that we're running. So I just want to emphasize that we're looking at the black box setting because in practice, we work very hard to come up with a differential privacy guarantee. We don't need to work even harder to come up with additional assumptions that would help us control the sensitivity of the hyperparameter quality. Okay, so let's start formulating a precise problem that we can solve. So as a start, we'll just assume that there is a discrete set of hyperparameter choices. So as I showed in my preview, there's going to be a set of algorithms M1 through M sub M. And we're going to assume that each of those is on its own differentially private. Again, this corresponds to a non-adaptive search because I'm just saying these algorithms are being pre-specified. And the ideal behavior, so the behavior that will get us the best utility as we're sort of thinking of the problem, is that our final algorithm A runs each of these, and it outputs the best value that is generated from those M runs. So one thing I want to emphasize is that, so for the exponential mechanism, you would not output the whole output of each of these M's. You would just select the index. So if I were to apply the exponential mechanism to the setting, I would just output the index J of the algorithm M sub J that produced the best value. But we're allowing you to return additional information. So we're allowing you to return the entire trained model if you're doing different machine learning. So we are allowing you to include more information than you would in the standard selection setting. So the obvious question now is this private? Is this a good approach? Now, as I mentioned earlier, if I just ran the composition over these M algorithms, I would get that this algorithm A is M times epsilon differentially private. So the question is, can we do better than that? Because I think in practice, M could be reasonably large, and we don't want to have our privacy parameter blow up that much. Any questions?
Thomas?
Yeah.
I had a question, which is, so do we have to release the hyperparameter itself or not? I understand we release the output of the model with the hyperparameters that we have chosen, but do we release the hyperparameter itself?
Good question. So I'm just going to assume that the output of the algorithm M includes the hyperparameter. So like, given the output of MJ, I can determine what J is.
It
there's sort
has
of
to be
like there's so yeah, I mean, this is sort of like without loss of generality because there's just no cost in doing this, and I can always just append this to my output, and it's just a lot notationally cleaner if I just say there's some output space y.
Okay, thank you.
Okay, so I've told you what the ideal behavior is, so why don't we just see if that works? So it turns out that this doesn't work. And the counterexample is fairly simple. So this was also observed by Liu and Talwar. So let's just assume that each of those algorithms, M sub j, is randomized response. Right? So if I input X, I'm going to output a 0 with higher probability. If I input X prime, I'm going to output a 1 with higher probability. Okay, so I'm going to run M copies of this, right? All of the MJs are the same. I'm going to output the best. So in this case, 1 is the best. And now we can calculate the probability of these outputs. So the probability that A outputs 0 is just the probability that M outputs 0 to the power of M. I guess when I'm saying this, the choice of M and uppercase M and lowercase m is not so clear, but I hope you can understand. And we can do the same calculation on the input X prime. So again, we take the probability that you output 0 and we raise it to the power of n, right? The only reason A would output 0 is if each of the little m runs outputted 0. Okay, so this is a straightforward calculation. Tells us everything we need to know. And we can just look at the ratio of these two quantities. So the denominators cancel, and we just get a ratio of e to the epsilon to the m. So this new algorithm A is at best m times epsilon differentially private. In other words, we don't beat composition. So this ideal strategy of just running everything once doesn't get us any kind of improvement. Does that example make sense to people? Okay, so let's start talking about the positive results. And I've given you this simple example. You may be wondering, like, how can we possibly end up beating composition in this setting? Now, the good news is that this negative example I showed you is pretty brittle. And there's a standard way to, there's an easy way to get around this. This is the approach that was suggested by Liu and Talwar, which says instead of repeating the algorithms a fixed number of times, so in the case I just said the M algorithm is going to run each of them exactly once, instead I'm going to run them a random number of times. And it turns out that just a little bit of randomization here is enough to sort of fudge these two numbers to get you a lot better privacy. So Liu and Talwar suggested the total number of runs should follow a geometric distribution, and that gives you this 3 epsilon result. And what we're going to do is we're going to look at a bunch of different distributions, and we're also going to give some results that look at Renyi differential privacy, which gives you some more fine-grained control of what's going on. Okay, so let's go back to, oh, was that a question?
Yeah, so at the beginning of the talk, you mentioned the self-report, the score. Is this fair to assume that the score is deterministic, or it seems like the self-report, the score should be randomized, right?
I mean, in this case, it's just randomized response, so the score is equal to the response. I think this example works fine if you think of it as being like some kind of Laplace being added to the value.
Okay, thank you.
Okay, so let's go back to the problem formulation. So again, we're going to start with a set of algorithms, each of which is differentially private on its own. And the actual behavior is going to be as follows. So we're going to pick some big K from some distribution, which we'll get to later. As I said, one example is the geometric distribution. But now, how do I, so I'm going to basically say I want to do k runs. How do I actually choose which algorithms to run? So the way we're going to do it is I'm just going to pick indices j1 through jk uniformly at random. And I'm going to run m sub j1, m sub j2, and so forth. So there's also some randomness in which ones I choose to run at each time. That's not really the essential part. But that's sort of how we're going to make sure that it sort of fits together, this random number of runs. Now, the key thing is, as long as the total number of runs, k, is larger than m, I mean, we want to have a bit of space, that may be a logarithmic, like m log m, then this should deliver good utility for us, because with high probability, at least one of these j's is going to select the value we're interested in, the good value, and we're going to run that m sub j, and we're going to hopefully output that good value. So this behavior is sort of reasonably well defined, and as long as that distribution is nice, we're going to get good utility.
Thomas, I have a question.
Yeah.
In the setting I'm thinking of, there's like, a huge number of possible hyperparameters. If I'm like thinking like training a neural network, and far more than I could ever hope to run. This will still apply to that setting, right?
Yeah, so I mean, we're going to have to select a discrete set of options, or just have some random sampling strategy for that discrete set, or you could have an infinite set of hyperparameters and just have some kind of sampling strategy for them. But yeah, this applies for like any size domain, right? You just have to make sure.
But we just wouldn't be able to give a nice guarantee.
Yeah, so I mean, the thing that's not nice about this is that I can't give you a guarantee. Yes, we definitely tried each of the settings. Like we only give high probability guarantees.
Oh, thanks.
Yeah, so the biggest question obviously is like, what distribution should we apply here, and what makes this work? So I'm going to give you a third, and this is the final version of the formulation, which is a little bit cleaner notationally. So instead of thinking of having some discrete set of options, I'm just going to think that there's a single algorithm, and we call this Q. Q is the notation that you and Talwar use, so we copied that. And basically what this algorithm Q does is if you run Q once, it will pick some index j and run one of those mj's. So now the final algorithm A is just going to pick k from our distribution, run Q repeatedly k times, and output the best. So this is just a little bit notationally cleaner to have a single algorithm Q rather than m1 through mn. And in this case, it sort of hides the fact that we no longer have to have a discrete set. All I need is that you have some kind of sampling strategy from your set of hyperparameters that you're searching. And we can talk about what exactly it means to have good utility in that setting. But now that we have this, the way we can sort of think of this is that you have some base algorithm that has some small probability of success. And we're trying to boost that. We're trying to sort of repeat the algorithm and get the higher success probability coming out. So this is the problem formulation that we're going to work with. Okay, so what distribution am I going to have for the number of repetitions? So the first question obviously is, what are the properties that we need? So as I mentioned, for the utility front, we just want that k is large with high probability. What's not so clear is what we need for privacy. So I'll get
Thomas.
Yeah.
A question. So the case where, so in this case, we may end up running each algorithm in the set of AM algorithms multiple times, right?
Yes.
So is that like a good case or a bad case? Because like I'm trying to like visualize that in the original algorithm, the baseline algorithm, we end up paying m times for composition, but here we end up running all algorithms multiple times. So like, am I missing something?
Yeah, so definitely there is that issue that you could be running the algorithms multiple times. So it's a problem from a runtime perspective, right? Because if you're running the algorithm too many times, you're going to run forever. And the other issue is that there's a chance that you'll have like an erroneous high score, right? Like the final quality score that you report has to be noisy. And there's this chance that that noisy value ends up being quite large. And as a result, you sort of end up outputting a thing that's true quality is lower than it should be. So if you run these things for like forever, for infinitely many runs, you're just going to get these weird tail things being picked up.
I see. Okay.
But I mean, in general, it's not a, I mean, as long as we're running everything, like hopefully it's a well-behaved algorithm and running it more than once is not a problem. But if you really look at the tails of the distribution, it is a problem.
Okay, thanks.
Yeah, so vaguely what we need is that the distribution has some kind of smoothness. So the problem is if you have a fixed number of repetitions, or you just run it a fixed number of times, that's a very non-smooth distribution. It's a point mass. So we need a distribution that is smoother than that. This is just a vague intuition. I'll give you a precise result right at the end of the talk. It ends up depending on what's known as the probability generating function, which is something I'd never heard of before working on this. But basically, it's the expectation. So the function f of x is the expectation of x to the power of k, where k is some random variable supported on 0, 1, 2, 3, 4. So like the Taylor series of the function f corresponds to the probability mass function of your distribution. So this function ends up being the thing we need to look at. When you kind of look at its derivative and sort of show that it's smooth, that gives you the right behavior. So the specific distributions that we have results for are the negative binomial distribution. Again, I was not familiar with the negative binomial distribution before we looked at it for this. It is a reasonably natural generalization of a geometric distribution. So if I take two geometric distributions and add them together, I'm going to get a negative binomial distribution. I could also do the opposite, where I have like split the geometric distribution into two distributions, each of which is a negative binomial. So it's kind of like a infinitely divisible family that corresponds to the geometric distribution. And we have some results for those. And we also look at the Poisson distribution, which is kind of like a limiting case of negative binomial. And we have some results for all of these. So I'm going to leave the generic results right until the end because they're a little bit hard to parse. But for a warm-up, we're going to look at the pure DP results first. Okay, so here is the result that we have for pure differential privacy with a negative binomial. Now it's a truncated negative binomial, which just means I'm going to take 0 out of the support. Okay, so here's the statement. So we have some base algorithm Q. This is the algorithm we're trying to boost the success probability of. I'm just going to assume a pure epsilon differential privacy guarantee. We're going to have K be drawn from this distribution, which has two parameters, eta and gamma. I'll tell you what the distribution is, but it doesn't really matter. There is an expression for its expectation. Again, it doesn't really matter exactly what this is, but just sort of gives you some intuition for what these parameters are. Basically, the mean is 1 over gamma times some constant that depends on this other parameter, eta. So we can think of eta as being a constant, and then gamma, 1 over gamma is the mean. Okay, so we have the algorithm A, which runs the base algorithm Q repeatedly, K times where K is random, and outputs the best. So this is going to be 2 plus eta epsilon differentially private. So you can sort of see this parameter eta controls how much I pay as a multiplicative factor in the privacy. So the prior work by Liu and Talwar is just setting eta equal to 1. And in that case, the negative binomial distribution is just the geometric distribution. And then we get a 3 epsilon. And in our case, we can actually take the limit as eta goes to 0. And this gives you what's known as the logarithmic distribution. And that gives you the result that I claimed right at the beginning of the talk. Any questions before I actually tell you what the distribution is? Okay, so what is this weird distribution that we're using?
Sorry, there is a question. Sorry.
Oh,
just very quickly, I want to is the statement accurate? Are you saying it's more private to possibly run everything multiple times, except you possibly miss something, and then release the best score, as opposed to running everything exactly once and releasing the best score?
sorry, what's the, I don't fully understand. So it's more private.
I'm saying, so just to understand what even the takeaway of the result, it is more private to run. You run this mechanism queues, you pick things at random, and in practice you end up running every mechanism from your set multiple times, but there's a small probability of missing something.
Yeah,
And that's more private than possibly just choosing to run everything once and picking your best thing. And the other thing is
yeah.
private, but I see.
Yeah.
Okay,
So
I see. Thank you.
yeah. So sometimes running things more is actually good for privacy. So if we go back to the example that I gave you, where running things a fixed number of times is bad, the bad thing is a very low probability event, and basically I can substitute. If I run more times, I'm sort of more likely to see a 1. And this bad event actually kind of goes away. It's a very vague intuition, but so sometimes running more times actually ends up sort of obscuring the bad event. Okay, so let me tell you what the negative binomial distribution is. So here is the formula for its probability mass function. This is the most uninformative formula I can really think of. It doesn't really tell you that much. I also have the formula for the expectation. Again, this is not very informative. I just wanted to put this here for completeness. But let me just sort of give you some high-level properties of this distribution that maybe helps you get you some intuition. So if I set the parameter eta to be 1, I'm going to get a geometric distribution. That's a distribution I hope we're all sort of familiar with. And if I take the limit as eta goes to infinity while keeping the mean fixed, I'm going to get a Poisson distribution. Now, this is actually kind of analogous to a binomial, and that's kind of where the name comes from. So in both cases, if you take a binomial with a fixed mean and take the number n to infinity, you're also going to get a Poisson. Now, there's a star here because it is truncated, right? So the normal definition of the negative binomial doesn't include zero in the support. And here we're taking 0 out of the support. And the reason is just that I don't want to run my base algorithm 0 times. That would be extremely bad. And I don't know if you're familiar with the gamma distribution, but this is really just a discrete analog of the gamma distribution. And there's actually a very precise way in which it is an analog. So one way I can generate a sample from a negative binomial is by sampling from a gamma distribution and then sampling from a Poisson distribution with the parameter that I drew from the gamma distribution. So it's kind of like a convex combination of Poisson distributions. Now, again, I don't think it's super intuitive what this distribution is, but here it is for completeness. And I'll right at the end, I'll sort of tell you how we came up with this distribution. Okay, so that was a negative binomial. Let me tell you about the Poisson distribution, which is another very natural thing to look at, because it's a limiting case of the negative binomial. So again, we have some base algorithm, which is epsilon 0 differentially private. But now I'm going to make a second assumption. I'm going to assume it's also 0 delta differentially private. So I'm going to have delta being a bound in the total variation distance. So I'm going to make these two assumptions. And now we're going to draw K from a Poisson distribution with mean mu. And we define the algorithm, the repeated algorithm A again as before, right? We repeat a random number of times K and output the best. And then this is going to have a pure DP guarantee where you have epsilon, so the original epsilon plus mu, the mean number of repetitions, times this delta parameter. So delta is always at most epsilon. We can always bound the total variation distance by the max divergence. So the good thing about this result is that the Poisson distribution is really nicely concentrated, unlike the negative binomial. So this is actually a nicer distribution to work with. The bad property here is that you are getting a privacy bound that still grows linearly with the number of repetitions. So this privacy parameter here grows linearly with mu. Now it is an improvement over composition because we're multiplying that mu by this delta parameter. So hopefully your algorithm has a small value of its total variation stability, so 0 delta dp. And that means you're going to get something that's growing linearly but slowly. And then what I'm going to tell you is that under Renyi differential privacy, so we're going to look at that later, we are able to get a sharper analysis of what's going on here. This is just the pure DP analysis. Yeah, so I want to just emphasize that this does beat naive composition. Any questions?
Question.
Yeah.
So how the distribution affects the privacy guarantee? So my question is like, does the benefit for privacy comes from like the resembling of the choice of the hyperparameters, or it's because like the running time, sorry, not the running time, the K is a random number.
Yeah, right. So I'll talk about that a bit soon. So K determines the privacy, as we can see from these results, but it also determines the utility, and there's kind of like a trade-off there. And again, like the kind of utility you want also depends on what sort of hyperparameter search you're doing. So like, there's a number of moving parts to consider. So let me, so hopefully,
Thomas, one question, sorry. So how does the success probability depend on mu? Like, I'm wondering, like, how we
yes, so
mu parameter.
So the success probability, so Poisson is actually very nice because if we go back to this setting, we have M algorithms I'm trying to run. If the total number of runs is Poisson mu, then the number of times I run each algorithm is Poisson mu divided by M. So the probability that I miss an algorithm, so the probability I run any given algorithm 0 times is e to the minus mu over M. Okay. So this is like this is very good. Like Poisson is very nicely concentrated. So we're getting some, like from a utility perspective, there's a really great distribution. From a privacy perspective, it's not quite so great.
I see. Okay, thanks.
Okay, so you're probably wondering like how did we end up beating composition? So I want to just give you some intuition for that. So the way I want to give you that intuition is by revisiting the example that we had earlier of randomized response showing that a fixed number of repetitions does not beat composition. So let's just like go back to that example and work things out again. And this is not a proof, but it does capture a lot of what's going on in the proof. So again, we have a base algorithm that's just randomized response. So if you put an X, you're more likely to output 0. If you put an X prime, you're more likely to output 1. And again, we're going to repeat this some number of times to output the best, but now the number of repetitions is random. And we're going to do it from a Poisson distribution. Okay, so the probability that this final algorithm, A on X, outputs 0 is the probability that Q outputs 0 to the power of K. And now K is random, so we have to take the expectation over this. Right, so this is exactly the same calculations we did earlier, except previously K was just a fixed number N, but now it's a random number. And we can do the calculation, and this is where the Poisson distribution is coming in. This is exactly equal to exp mu times this number minus 1. We do the exact same calculation for the case, probably that A of X prime output 0. Again, we go to exp mu times this number minus 1. And then we look at the ratio of these two quantities. So we look at the log of the ratio of the two quantities. Now, previously, this was m times epsilon. And now you can work it out. It is this quantity, which, so for small values of epsilon, it's just a half mu times epsilon. So this beats composition by a factor of 2, right? So mu is the average number of repetitions. It's nicely concentrated, so it should be, it's pretty closely analogous to just running at a fixed number of times mu. So this is a simple example, the simplest example I can fit on one slide, which shows that we are able to beat composition. And kind of the magic is just that this function here, exp mu times x minus 1, is nicer than x to the m. All right, so previously we had a fixed number of repetitions, we had this monomial x to the m. Now we have a Poisson, we get this exponential function. Now these functions are known as a probability generating function, which I briefly mentioned earlier. And what's happening here is that this probability generating function is just a little bit smoother, and therefore we're able to get a little bit better privacy guarantee. Now, as I said, this is not a proof. This is just sort of showing how the previous example breaks. The proof kind of looks like this. Now, when we look at the negative binomial distribution, instead of this function x mu times x minus 1, I get something messier. So I didn't work that out. We get better results, so we don't have this linear dependence on mu at all. So it's just a matter of choosing a distribution that gives you a nice function here. Does that make sense? Okay, so that is kind of like the best I can do in terms of getting some intuition for what's going on in the proof. Okay, so let's change tack a little bit and talk about the
Thomas, before you move on, could you give us some intuition for how you ended up with like these two distributions, the negative binomial and Poisson? I mean, like,
so okay, yeah, that's a great question.
Like magic right now.
That's great. Okay, yes, that's a really great question. So the answer is, I looked at this proof and I said, okay, I want a different function here. So I'm going to pick the function and then work out which distribution gives me that function. And how did I come up with the negative binomial? I mean, I looked at the function that the geometric distribution is. So the prior work, Liu and Talwar, had geometric distribution. Work out the function. It's basically something that looks like 1 over x. There's some annoying terms in there, but it's basically something that looks like a 1 over x. And I was like, well, what happens if we put in like a 1 over x to the eta? You just change the exponent, and that gives you these negative binomials. So it is magic, but basically, like you say, look, here's how the proof looks. There's this function that comes up. I'm going to change that function to work better for me.
All right, thanks.
Okay, so
hi, Thomas.
Yes.
Hi, this is Robin speaking. I'm really sorry. I think this is going to be a very stupid question, but on this, it's about this example. Could you explain to me how does it? So A is basically running Q for a random amount of time.
Yeah.
That is distributed K Poisson, and my question is how does so the fact that you're choosing a best output among the K times of Q that you run, is that going to still be the same as thinking that A is a composition of K times, or is there something more than just that?
So it's not just applying composition. So the way it works is you just work out what these probabilities are. So here we have, how do you work out the probability that you output a 0? That's just, you take the probability of the base algorithm output 0, raise it to the K. More generally, if you think there's some like larger set, so here I just had 0 and 1. But if you have a larger set, you can say, well, what's the probability I output something that's less than I'm running out of variables, less than A. No, we're already using A. Less than C. So I fix some C and I say, what's the probability that I output something that's smaller than C?
Oh, I see. So basically that criterion is chosen so that determines good. So you want it to be less than something, and then you want to try, say, K times so that you reach that threshold. That's the idea?
Yeah.
Cool.
Right. I mean,
thank you.
Yeah, so I mean, basically, like the idea of repeating and outputting the best, it's like very naturally interpreted in terms of the like CDF of the function of the distribution. It's like just take the power of the CDF, and that's like that's what we're doing here, just with the special case of 0. The more general case, the actual proof just says, okay, we're going to look at the CDF at an arbitrary point. We get an expression exactly like this. And then we get this function coming in from the expectation over K.
Right. So essentially, this is kind of, to make an analogy, this is kind of like when you do multiple testing, and then you're trying to hit a particular threshold, but now you're planning for the fact that you're going to repeat this K times and pick the best one that exceeds the threshold, which is
I mean, like the threshold is only in the analysis, right? The algorithm doesn't have a threshold. We're just we're going to analyze every possible threshold.
I see. Thank you.
Okay. So the question is utility, right? So we've talked a lot about these privacy guarantees. How do we even measure utility? Because we've got this base algorithm that runs some number of times. It has some utility. We're going to repeat it, take the base. Like, what does that mean for any reasonable measure of utility? So like just at the high intuitive level, we just want K to be large, right? Because if K is large, it means we're doing many repetitions. We're likely to find the thing we're looking for. Now the obvious thing that you would think of to measure utility is just the expectation, right? So that's kind of like a first order approximation. The higher the expectation is, the better we have utility. The problem with this is, what if your distribution is really heavy-tailed? So like, as an extreme case, let's imagine I have a distribution that is 1 with probability 1 minus p, and 1 billion with probability p. So the expectation of this distribution is really high. But if I actually run my algorithm this way, like with high probability, I'm just going to run my base algorithm once. So this isn't really helping me. And now this isn't formally a heavy tail distribution. I mean, I said it's bounded, but this is kind of the thing that we want to avoid. So another type of thing we might look at for quantifying the utility of the algorithm is some kind of binary success probability. So let's just imagine the base algorithm has a 1 in m probability of success, and otherwise it fails. So it's like a binary outcome. So this is the case where you're looking through a set of M hyperparameters and just like one of them is good, everything else is terrible. Now you can work out the probability that this final algorithm outputs something good. So basically it's 1 minus the probability that outputs that it fails, which is 1 minus 1 over M to the power of K. So this gives you a formula that says I have an initial success probability. What's the success probability of the final thing? So there's another thing that we could look at as a measure of utility. The problem with this one is that you have an additional parameter M. So we're looking at these additional things that are going to kind of make it harder to compare. So actually the thing that we decided was the cleanest representation of utility is what we call the expected quantile. So you can think of the distribution of a single draw of the algorithm Q as having a quantile that's uniform between 0 and 1. So like by definition, you're going to have some quantile between 0 and 1 that is, I mean, basically the quantile is you apply the inverse CDF. You apply the CDF. Now, if I were to repeat it a number of times K and take the maximum, the quantile is going to be a beta distribution, which has mean K over K plus 1. And basically, the expected quantile is just going to be the expectation of K over K plus 1, or 1 minus the expectation of a 1 over K plus 1. So if K is large, obviously this is small. But this is kind of a nicer measure of utility than the expectation, because if K is equal to 1 with 50% probability, then I'm going to get a 1/2 here with 50% probability, and there's like it sort of hides the heavy tails. So I could have as heavy a tail as I want. I'm still not going to get past the fact that I, with decent probability, have a very small K. Okay, so these are the different ways that we're going to just sort of measure utility in a generic sense. So let me show you some plots. So here I have a plot. Now the base algorithm here, I'm just going to assume that it satisfies 0.1 ZCDP, so it's concentrated differential privacy. And this is the kind of guarantee you get if you added a Gaussian with variance 5 to a sensitivity 1 statistic. And it, just as an application, it gives you like 2 10 to the minus 6 differential privacy. So if you're not familiar with what this is, just sort of think of it as a reasonable privacy guarantee. A lot of real world algorithms kind of are at least well approximated by concentrated DP. Now the plot is using our results for Renyi DP, which I haven't told you yet, but it converts them back to approximate DP, so you don't have to think about the world of Renyi DP. And so basically on the horizontal axis, I have the epsilon that we get. And on the vertical axis, I have the expected quantile, which is a measure of utility. So where we'd like to be, obviously, is up here in this corner. Like this is good privacy and perfect utility up in the top left corner. We start out in the bottom left corner. That is just one repetition. So if the base algorithm is this corner here, it's 2.14. So epsilon equals 2.14. And its expected quantile is a half, 0.5, because it is uniform 0, 1. But basically what these lines are saying is I'm going to increase my privacy budget a little bit by allowing some repetition. And as a result, my utility is going to go up. And each of these different lines corresponds to a different distribution. So why don't we start with a Poisson distribution, which is the purple line. So as we can see, it rapidly, so in this intermediate range here, so we've blown up my privacy by my epsilon by like 50%. I'm getting, this is kind of like the best distribution. But if I actually want to have a very high expected quantile, it is beaten by these negative binomials. So then we have a bunch of different negative binomials. So it turns out you can actually set this eta parameter to a negative number. And this plot shows why you don't want to do that. Like setting eta to a negative number does not get you any good results. So we're not going to do that. I just wanted to show that to you because we technically can do that. And now we have a bunch of different lines that correspond to the negative binomial. So the eta equals 0 line is this dark blue line. That's the logarithmic distribution. As you can see, it doesn't seem to really beat out any of the other distributions. So this is one that you probably actually wouldn't want to use. And the reason is because of these heavy tails. So the logarithmic distribution has really heavy tails. The mode of the distribution is always at k equals 1. Now, obviously, just being the mode is not too bad because it's still a low probability event if I make the expectation high. But the issue is that even if the expectation is very large, there's still a decent chance that you've got a very small value of k and you're not doing enough repetitions to see what you want. But if we increase this parameter eta even a little bit, we are able to start avoiding these heavy tails. So the logarithmic distribution is sort of like a uniquely annoying distribution with its heavy tails. If we start increasing the eta parameter, we start getting better behavior. So the orange line corresponds to eta equals 0.5. And as we see, this gets you pretty good privacy utility trade-off. So the range we're usually interested in is up here. We want to get something that's in the 99th percentile if we're searching of a set of size 100. We're getting the best privacy guarantee for that kind of utility. But something I should point out is that no distribution dominates any other distribution here. Like there's no distribution where I can say, oh, this distribution you should never use because there's some other distribution that's better. Although, the regime of interest, probably the orange line would probably be the most interesting. But we also see the Poisson does quite well in this other range. So does this plot make sense to you? This is just sort of trying to give you a comparison of what these things do. Okay, so that was the expected quantile, which I consider to be the nicest way to summarize the utility in a single number. I mean, obviously it's an entire distribution, but that seems to be a clean one summary that we can plot. So let's look at some of the other things we talked about. So look at the expected number of runs. So this is exactly the same setup. So the base algorithm satisfies concentrated DP. We're converting to a prox DP. All I'm changing is that the vertical axis is the expectation on a log scale. I guess I also changed the horizontal axis by like making it go to 0 rather than starting at 2.14. That's just so the legend looks nicer. So we're seeing it, this looks very different to the previous plot, right? So on this plot, if we're just looking at the expectation, the logarithmic distribution looks really good. Right? Like this is the one that gives you the highest expectation for any given privacy budget, except for like very small privacy budgets. And what's happening here is the heavy tail. So like we're getting a huge expectation, but that's because there are very heavy tails on that distribution. Now again, this is not formally a heavy tail distribution. We have to like kind of formulate that a little bit differently, but basically, even though you have a very high expectation, we didn't actually get a high chance of success because there was still decent probability of k being small. Okay, so now this is the other. Oh, sorry.
Sorry, I just need to interrupt you because I think the sort of past the 1 hour deadline that we had. I understand that we interrupted you without question, but I was wondering how much time do you need to wrap up?
Wow, we've actually gone through the hour. I can just kind of skip to my conclusion in like 2 minutes about that. I still have more things I wanted to say, but let's skip over those.
Yeah, I think It's fine from our end. Just yeah, just want to let you know. Thank you.
Okay, yeah, sorry, I wasn't even keeping track of the time, so thanks for telling me. Okay, anyway, so this is the same setup again, but now we're going to do the success probability. So we say we're going to look through 100 options. We either find it or we don't. Now in this situation, now we see a similar graph to what we saw before, except now the Poisson does really poorly, just because the privacy analysis for the Poisson is not as tight as we'd like it to be. We also have a plot that has some like actual experiments with like training a deep neural network. I don't have like any real conclusions from this other than to say that like this looks exactly what the theory predicts. But it's kind of noisy because this is actually a simulation, even though we average over 500 runs. You can see these lines are still quite noisy. Okay, so I'm just going to skip over the Renyi DP and go straight to the conclusion since we're running it over time. I did not anticipate that. Okay, so let's just wrap up. So the positive results, I showed that repeatedly running an algorithm that is DP and only reporting the final outcome does have lower privacy costs if you do it right. So you have to be careful. You have to make sure you run each individual run is differential private. You have to make sure that you randomize the runs. You don't have to do too much randomization to get good results though. And the Poisson distribution is not that far from a point mass, but it's still giving you a significant improvement. And again, we accompanied this with some negative results that show that if you aren't careful, if you don't do it right, you are going to have some costs there. So the analysis, it's basically an improvement in generalization of what Liu and Talwar did. We looked at more distributions, and we also sort of gave a generic result, which I haven't actually told you about, that relates probability generating functions to what we're interested in. Some important questions for future work is, are there other distributions to look at? I mean, I think we did a decent job of exploring the space of possible distributions, but we don't have any lower bounds. We don't know these are optimal, and there could be other distributions we could try. And as was mentioned earlier in the talk, it'd be really great if we could understand an adaptive hyperparameter search. This is just a non-adaptive search, and I think there's still some interesting questions there. And the other thing is, we assume this is a black box, so we just assume that the algorithm is differentially private. We didn't look inside. I think it'll be interesting to look at some special cases. We could do better. Maybe we can basically show that it's kind of like a low order term. The privacy doesn't blow up at all except for a low order term. That'd be the ideal. Oh yeah, thanks.
Any question for Thomas?
Yeah, one question. So do you have or can you give some intuition as to why the algorithm kind of breaks down when we're looking at the adaptive regime?
I mean, I just haven't thought about the adaptive regime. I think like the formalism just totally breaks down. I'm just not even sure how to formalize it. I don't really have an intuition. I mean, I guess the issue is this like garden of the forking path. So even though I only tried adaptively 5 things, this could kind of correspond to a non-adaptive search of a 2 to the 5 things, right? So there is some sort of room for blow up. I mean, we have like interesting results for adaptive data analysis. Maybe those sorts of things will carry over here. Maybe there is a separation.
And you need to rule out stupid things like the next run of the algorithm keeps around the previous runs of the algorithm.
Right. Like it seems like you could easily come up with an example that would just boil down to composition.
Do we have any hope for like a better guarantee when the privacy for each algorithm has a different privacy bound other than taking the max?
So I think the way to do that would be to kind of, so let's say some of your algorithms are epsilon dp and some of them are 0 dp, then this would kind of correspond to privacy amplification by subsampling. So I feel like that might be the connection there. Obviously, it's not going to be 0 versus epsilon. It's going to be some distribution, some going to be epsilon, some 2 epsilon. So it'll be like a fancier version of privacy amplification by sampling.
Cool. Thank you. Great talk.
Question, if you have time. Do you have time? Yeah. Okay, cool. I was just wondering, suppose you have some n objects, right? And you want to privately pick the one with the best score.
Mm-hmm.
I understand. And suppose that one way that you can like apply the algorithm you just described is like every time you query the score of an object, you just get randomized response, right? Is there, do you know if like there's a regime of like for some choice of epsilon where your algorithm would beat by doing this would beat, let's say, the exponential mechanism or like for mutant flip?
Yeah, so these results definitely they can be applied to the like standard selection problem. They do, I mean, like we can't beat the exponential mechanism because we have lower bounds for that. And like we don't beat them on the constants, right? Like there's possibly some room for improvement on the constants, but we don't, you know, the constants we get from this conversion are not great. So there is actually a paper by Yuxiang Wang and what's her name? Shuxing, I'm screwing up the name, which actually looks at a question kind of like this. They look at like a Renyi DP version of the sparse vector algorithm, and they get results that are actually very similar to what we have here. So they, for example, you can use Gaussian noise for sparse vector. You can use kind of like in our work, you could use like a Gaussian noise version of the exponential mechanism or report noisy max. As far as I know, it doesn't like actually beat the standard results, but I think there's possibly some room there for exploration. There might be some regime where it does beat it.
Thank you.
Any other questions?
I have one more nice question. I'm trying to think what the optimal distribution would be like, and I realized I think I'm not sure what we mean by optimal. Because utility, isn't this what, did I understand this correctly? The utility could be, like there's different optimal distributions if we talk about utility, the way we measure utility. But there's an optimal distribution in terms of privacy loss at the end. Is that what we would?
So I don't even think it's like I don't even think there's an optimal distribution in terms of privacy loss, because it sort of depends on. So if you go into the Renyi DP regime, which I didn't actually manage to talk about, you're going to look at not just a single point on the Renyi DP curve, but multiple points at the same time. So different algorithms will have different curves. Right, so if you started with something that is like the Gaussian, so that has concentrated DP, you're going to get one kind of result. If you started with something that is pure DP, you're going to get a different kind of optimal result. So I really have no idea what an optimality result would look like in this setting, just because there's all of these like different potential applications where one distribution might be better than another, and a different application it looks different, both from the privacy analysis and from the utility. So yeah, it's like it's the super rich space to look at.
I see. Thank you so much, and great talk.
Thanks.
Any other questions? Okay, so let's thank Thomas one more time.
Okay, thanks for inviting me.
Thank you for accommodating us in this inconvenient time for you. Sorry that we had to, you had to change your plans.
Oh, good.
Appreciate it. Thank you for the great talk.
Good to see you all.
Yeah. Have a good day.